Hello everyone, my name is Madeline Janecek, and I am going to be talking about how we achieve container workload characterization using host system tracing. So over the course of the last couple years, containers have been becoming more and more popular in different production environments. And this is because of their lightweight, scalable, and efficient nature that makes them suitable for cloud environments. That being said, monitoring is still among one of the top challenges with container use and deployment, especially considering how thousands of containers may be running simultaneously on a single server. In our work, we set out to achieve three main goals. The first of these goals being that we wanted to generate a fine-grained characterization of container workloads. Many existing container monitoring solutions rely on things such as resource utilization metrics. We wanted to explore data sources that could create a more precise and detailed picture of container execution for a more precise analysis overall. We also wanted to develop a manageable solution that can easily monitor many containers. As previously mentioned, thousands of containers may be running on a single host, so we wanted our solution to be generic in that it could be applied to several different types of containerized applications. We also argue that by clustering different containers based off of their workloads may help system administrators to be able to deal with issues and the needs of different containers on a group-by-group basis rather than having to go through them individually. We also wanted to make sure that we developed a non-intrusive host-based monitoring. That way, the level of instrumentation needed for our methods is minimal. To achieve these goals, we turned to kernel execution tracing, and tracing is already a well-established tool in different kinds of software analysis, including performance anomaly detection, root cause analysis, and program execution comprehension. Execution tracing basically just consists of collecting different time-stamped events that can then provide a very detailed picture of system execution. So we can see threads, what states these threads were in throughout their execution, inter-thread interactions, how these threads interact with different resources on the system, so on and so forth. These events could be system calls, scheduling activities, or interrupt handling, just to name a few different types. And at each event, we collect different metadata fields called contexts, so we can see what the event was, what process ID it belongs to, what CPU the thread was running on, so on and so forth. With a Linux kernel, we have these trace points pre-inserted, so there's no extra instrumentation needed for our approach. To perform this tracing, we use Linux Trace Toolkit Next Generation, which is just commonly known as LTTng. It's an open source software toolkit that can perform execution tracing on multiple layers, so we can collect information from the kernel level, network level, user space level, and it can collect trace events while imposing very little overhead to the system, making it ideal for our analysis. Just to give an overview of the overall approach, we start off with host trace collection. We then move into a data pre-processing phase where we perform thread ranking inspired by the PageRank algorithm. We also perform some data vectorization, and after the collected data has been prepared, we move into a two-stage clustering approach, that all of which is explained in the following slides. Based on our observations, tracing a containerized application is virtually no different than tracing an application that's just running directly on the host. We just want to ensure that we have three different contexts enabled throughout our tracing so that we can be aware of the different containers that are running. So each container has its own unique process namespace. So by enabling the process namespace ID context, we can group the events based off of their respective containers. We also want to make sure that we're collecting each thread ID, and this is just the thread's unique ID on the host. Similarly, it's important to have the virtual thread ID, which is just the thread's ID from the perspective of the container. Throughout its execution, a thread may be switching between several different execution states, and using the collected trace data, we can determine the ordering and duration of these state sequences. So we have two different running states, including system call mode and user mode, and these two states simply differ in the level of privileges that are required for that thread's execution. We also consider a couple of block states, including interrupted, preempted, blocked, and waiting. Interrupted occurs when an interrupt request occurs, and the thread must wait until the interrupt handling has wrapped up. Preempted happens when a thread is ready for its execution, but it must wait for an available CPU time slice. Block state occurs when a thread must wait for a certain condition to be met. For example, it needs to wait for the allocation of certain resources. And we also consider a waiting state, which is essentially the thread is just idle, which might occur, for example, when a thread has been created, but it has not started its execution. These states may be used to characterize a container's workload. For example, if we see an abnormally high level of preemption, this may be indicative of a CPU-intensive workload. If we see a lot of block states, this may be indicative of, say, an I/O-intensive or network-intensive workload, which is why we extract them for our analysis. After collecting the trace data and determining the execution states of the threads present in that data, we have to generate a single representation of each container so that we can cluster them based off of their respective workloads. It's important to note that each container is often made up of several different threads, and not all of these threads are necessarily active during the tracing session. So for example, on the screen is a screenshot taken from Eclipse Trace Compass, which is a very useful trace visualization tool. So in this view, the horizontal lines represent the different threads, and the different colors represent the different execution states. So the gray color there represents the waiting or idle state, and we can see that there are a couple of threads that remain idle on the screenshot, but they also remain idle throughout the entire tracing session. So considering these inactive threads may impact the analysis's accuracy, as it takes away from the more influential or important active threads. We also have to make sure that we standardize the representation of each container so that we can make a meaningful comparison between different containers. And this is what led us to consider ranking the threads based off of their relevancy. To determine a thread's relevancy, we use a slightly modified version of the PageRank algorithm. So this algorithm is commonly used in web structure mining to find relevant web pages to a given query. So it scores each web page's relevancy based off of the number of links pointing to that web page, as well as the quality of those links. So a page that has a lot of highly influential pages pointing to it will get a higher score using the PageRank algorithm. We consider the inter-thread interactions as links and a given thread as a page, and we use those to score each thread's relevancy, and we only include the most relevant threads in a given container when representing that container for the clustering algorithm, which is explained later on. To compute the relevancy of each thread, we start off by generating a directed graph where each of the nodes represents an individual thread. The directed edges between these nodes then represent the inter-thread interactions that we get looking at trace data. A simplified example of one of these graphs is shown on the screen, where the white circles represent a node, or in other words, represent an individual thread. As the number of links starting from a node increases, the weight that thread has decreases. So the weight of, say, a link starting from B would be less than a link starting from D. So in this example, thread A would be considered to be a highly influential thread that we would want to consider in our analysis, whereas the thread marked with C would be less influential and probably excluded from the analysis. So after determining the relevancy of each thread, we take the most relevant threads from each container and use them to create fixed size vectors. And this is because most machine learning algorithms, including the clustering algorithm that we use in our container workload characterization, expect fixed size vectors. So we generate state duration vectors. And these vectors have an entry for each of the possible execution states. Again, we have the 2 running states and the 4 block states. And the value of each of these entries is the total time that each of the most relevant threads spent in each of those states. After generating these vectors, we normalize them using the L2 norm. And this improves the clustering quality and overall efficiency. So just to help visualize this process, we have 2 different threads along a number line representing the duration, where each color represents a different execution state. So the state duration vector is a combination of the total duration each of these highly relevant threads spent in each of the execution states. So after the data has been pre-processed, we can move on to a clustering stage. So as previously mentioned, one of our main goals in this work was to develop a method that would work well with a large number of containers. So we argue that grouping the containers based on their workload will allow system administrators to save the effort of going through each of the containers and addressing their needs individually, and instead they can deal with the problems of a group of containers. One thing we wanted to keep in mind is that the grouping could not be reliant on labeled training data. This is because this information may not be readily available, and it would also constrict our approach's ability to discover new execution behaviors. This meant that we could not use, say, machine learning classification algorithms, as they were, for the most part, all reliant on this pre-labeled training data. This led us to explore the use of clustering algorithms to discover different container workloads. The clustering algorithm that we ended up going with is the k-means clustering algorithm, as it allows for unsupervised clustering of the state duration vectors. So k-means works by identifying k centroids, which serve as the cluster centers, and then it assigns each of the other entries to one of these centers based off of which one they're closest to. This is done with the overarching goal of maximizing the intra-cluster similarity as well as the dissimilarity between different clusters. One benefit of this is that we can use the centroids as a single representation of the workloads that we find within that cluster. One downside of the k-means clustering algorithm is that it requires that the number of clusters is declared beforehand, and this is not necessarily an easy value to determine. So to get around this, we use the silhouette coefficient, and the silhouette coefficient scores the clustering results where a high positive value indicates highly separated clustering. So because k-means is such an efficient clustering algorithm, we cluster the data multiple times with a range of k values, and we pick the results that result in the highest silhouette coefficient. So on the screen is a visual overview of our 2-stage clustering approach, which we do using the k-means clustering algorithm. So we start off with a coarse-grained characterization where we first cluster the data into 2 and then 3 groups, and then we take the results that give us the best silhouette score. It's important to note that we may get a better silhouette score if we use a different value for K, but we want to limit the number of groups we get in this first initial clustering phase to maintain the manageability of our approach. If we end up with too many clusters, it defeats the purpose of clustering in the first place. We then move into a fine-grained characterization phase, where we one at a time take each of the groups that we got in the first coarse-grained clustering phase, and we cluster each individual group using K values ranging from 2 to 10. We compare the results of the first stage clustering with the silhouette score of the secondary clustering, and we take the results that give us the best silhouette score. And this is just to further explain the first and second stages of clustering. On the left, we have the first stage of clustering where the items are broken up into 3 distinct clusters, and then we go through and look at each cluster to apply a second stage clustering, which creates smaller subgroups, resulting in a finer grained characterization. To test our method, we set up quite a few Docker containers, and we made sure that there was a wide variety of different workloads present in the environment, and then we proceeded to use our method to trace and vectorize each container and apply the 2-stage clustering method. And this resulted in 3 different groups, and as I mentioned before, we used the cluster centroids to represent the workloads found within each cluster. And we found that a first stage of clustering created 3 groups where the first group represented those containers set to have CPU intensive workloads. The second cluster had those set to network and IO intensive workloads. And then the third group it made were all of the containers that were set to run idle. And here we see the results of the second stage clustering, resulting in a finer grained characterization of the containers. The idle workloads did not benefit from any further clustering. There was no increase in silhouette score, and for that reason they remained one group. But on the left we see that the CPU intensive workload group was broken up into 2 subgroups, one of which had a higher level of preemption, whereas the other one had a higher level of system call mode, indicating that the workloads in this group performed more higher level operations than the other. On the right, we see the results of clustering the next group, and it just so happened that the 2 groups were broken up into IO intensive operations and network intensive operations, showing that our methods are able to distinguish between different types of workloads pretty easily. So in conclusion, being able to cluster fine-grained metrics that have been taken from host execution trace data to discover distinct workloads shows to be a very promising solution for monitoring a large number of concurrently running containers. If you have any questions on this work, we go into more detail in our paper, and we're also open to any questions you may have. So yeah, thank you for your time.